Hey guys, let's continue verifying trig identities. So we're here on example 5 now. Cosine squared x minus sine squared x equals 1 minus 2 sine squared x. There's a lot of different ways to solve this. One way would be that we could replace cosine squared with 1 minus sine squared. That's one of our Pythagorean identities. We still have this minus sine squared x equals 1 minus 2 sine squared x. Over here I've got a minus sine squared x and another minus sine squared x. Those are like terms, so 1 minus sine squared x equals 1 minus 2 sine squared x equals 1 minus 2 sine squared x. So all I had to do here was combine these like terms. Minus sine squared x and minus sine squared x is minus 2 sine squared x. Two sides are identical, so I've proven that the original statement is true. On example 6, what we'll do is square this binomial. So when I square a binomial, anytime I'm squaring a binomial, call it a plus b squared. That's the same as a plus b times a plus b. And every time it comes out to the first term squared plus the product of terms a and b doubled, so 2 times ab plus b squared. So I've got the first term squared, the product of these is ab doubled, and then the second term squared. So here the first term squared is 1. The product of these is minus 1 times tan theta. Double that is minus 2 times tan theta. And the second term squared is plus tan squared theta. Equals secant squared theta minus 2 tan, I'm going to run out of room, squared theta. So I've got a minus 2 tan squared theta on both sides. If I add 2 tan squared theta to both sides, that is going to cancel. So I get 1 plus tan squared theta equals secant squared theta. And one of our Pythagorean identities says that 1 plus tan squared theta is equal to secant squared theta. So I'm going to substitute this. For this, I'm going to substitute secant squared theta equals secant squared theta. My two sides are identical, which proves the original identity. In example 7, one of our Pythagorean identities is that 1 minus cosine squared theta is equal to sine squared theta. So I'm going to replace that with sine squared theta. In this case, it's actually x, so sine squared x over, and another identity is that tangent x is sine x over cosine x. So I've got sine squared, and I can just put that over 1 over sine x over cosine x. So when I multiply the outer loop, I get sine squared x cosine x, and that's my numerator. The inner loop is sine x. I've got a sine x in the numerator, a pair of them in the denominator, one in the denominator and a pair in the numerator. I can cancel out 1 sine x out of the numerator and the denominator, leaving me with sine x cosine x in the numerator and sine x cosine x in the denominator, and that proves that the original statement is true. And example number 8, cosecant b. Cosecant is 1 over sine, so that's 1 over sine b. And this one is sine and cosine already, so I'm going to leave that. And I'm just going to leave the right side alone for now and see what happens on the left side. So if I want to subtract these fractions, I need a common denominator. That common denominator is going to be cosine b times sine b. So I'm going to multiply numerator and denominator here by sine b, and the numerator and denominator here by cosine b. These cancel, so I get 1 over sine b cosine b minus cosine squared b over sine b cosine b. Now I can combine these fractions because I have a common denominator. 1 minus cosine squared b is sine squared b. That's one of our Pythagorean identities. I have a sine that I can cancel out of the numerator and the denominator, so I get sine b over cosine b. And one of our identities says that tangent b is sine b over cosine b. So my left and right match, and that proves the original statement is true.